Peter Woolfitt. I'm a senior in the math department, majoring in applied math with a minor in computer science theory. I should probably apologize to start with. I'm recovering from a cold, so we may be interrupted with a few coughing sessions. But I've brought a trusty hanky, so it should be okay, or more okay. This is going to be a fairly interactive talk. I want to go back and forth with you so we can discuss some of the ideas of what a proof is. And I guess I'll also have a few maybe slightly interesting problems. So first, let me ask the audience, what do you think a proof is? All right, I will, okay, I have to take it.
It's a way of showing that something that is not a fundamental truth or axiom is true based off of a set of fundamental axioms.
Yes, that is a good answer. So let me be a little bit more precise. There's sort of two things we mathematicians call proof. There's a formal proof and an informal proof. Which one do you think we use more?
Informal.
Indeed. It's a lot easier. Yeah, so a formal proof is, so, okay. To prove things, what is your name?
Austin.
Austin. Like Austin said, we build off a set of basic axioms and assumptions, and we make logical statements, or, yeah, so we make a logical progression of statements. Each statement follows from the axioms, the assumptions, and previous statements. And we reach a conclusion, and then we say we've come up with a proof. Alright, so we can do this very formally by building a set of basic axioms. So for like arithmetic, we have something called the Peano axioms. I'll delve into this idea a little bit more later. And so in formal logic, we use very basic steps. It's very hard to just read formal logic and understand it. In fact, it's very hard for most mathematicians to write formal logic. Yeah, and so mostly we just have formal logic as a backup, something we could do in principle but would never actually want to do in practice, because it would just take forever for like actually hard mathematical concepts. Okay, an informal proof. An informal proof is what we do most of the time. The idea is to convince yourself and others of a statement. And you do that by dealing with all the possible problems or elucidating why something is true. Okay. Let me go to my first problem. Perhaps one of the first problems you've seen. Classic. All right, 1 plus 1 equals 2. Do you guys believe me? Yeah? Okay, cool. Why do you believe me?
Because we've been taught that is true.
Right, yes.
Because we've arbitrarily defined 1 plus 1 to equal 2.
Sort of. It's not quite arbitrary, though. I mean, it makes sense to us, right? I mean, we have this thing is we're calling 1, this thing we're also calling 1, and together we're calling this 2. I mean, we have some also practical use with this statement. Okay, how do we go about proving this statement?
Show me that a plus a is 2a.
It's a little bit more general than this. We could, okay, so certainly if we could show that, then we'd be okay. But I would think that that would be harder than showing this.
Define equals.
Yes, I mean that's right. We have to define what we're talking about. We have to define what these symbols mean. We have to define what 1 plus equals and 2 all mean. Yeah, so this is where we use the Peano axioms of arithmetic. So we have some idea. So the Peano axioms of arithmetic say you have a 0 and you have a successor function. And the successor function just basically allows you to plug in an integer and get out the next integer, that integer plus 1. I'm not going to go into the details, but the idea is that with this basic system of axioms, you can prove 1 plus 1 equals 2, and prove the successor of 0 plus the successor of 0 is the successor of the successor of 0. Okay. But this is an example of something which we usually assume in our teaching as an axiom. We were, as Zane said, we were just taught it in school. It's how we approach this problem, through an idea of an axiom. All right. Now, you some potential problems with informal proofs. So I'm going to write an equation, and you're going to tell me, well, okay, let me just try. S equals 1 plus 2s. Oh, comma 1. Okay. Who can tell me what s is?
Variable?
Yes, yes. I mean, solve the equation. S is here a variable. Okay.
Is
okay,
this a
I'll
trick?
help a little.
One word.
S equals -1.
Okay, so let me subtract.
Jesus, I
S. I've heard the answer. It's -1. Right. Let me just go ahead and write out the answer. Yeah, physicists have skills too. 1 plus s, so I subtract s from both sides, and then I move to -1. Okay. Is this a proof that s equals -1?
Yes.
So are
Informally.
you convinced that s equals -1?
Yes, it's informal. I'm convinced.
Yeah,
That's
this
because you got it right.
seems like a fairly reasonable informal proof. Yeah, let's just call it an informal proof for now. All right. Now, are you ready?
He's about to go back.
Okay. Let me define. So okay, actually, let me just make a new variable so we know how to. T. Okay, so I have an infinite sum. I have 1 plus 2 plus 4 plus 8 plus all the powers of 2. So what does t equal? Infinity seems like a reasonable answer. I heard it over here. Yeah. Okay.
The partial sum of an infinite series?
Yeah, so we could take the partial sums, we could note that each partial sum is 2 to the n minus 1, and say the limit goes to infinity. All right, sure, so maybe t equals infinity. But consider this. So I'm just going to rewrite it. So I'm going to factor out a 2 out of the rest of this. Okay, do you guys agree with this?
No.
Maybe some of you see what I'm doing already. But okay, first you should see what I'm doing with this equation. Do you guys agree? Okay. So this part is something I've already defined. I've defined it as t. So we get the equation. T equals 1 plus 2t. All right, well, like we said, if we have this equation, I proved to you that -1 equals t. So you're all satisfied with this, right?
I
No.
think we would fail a test if we did that.
All right. Is this a proof that the sum equals -1?
No.
Why not?
Contradictory answers?
Yeah, it's not true. It doesn't convince you. It's not a good proof. I guess there's also a detail with something we call proof. We sort of associate the terms attempted proof and proof. You can write a proof of the question, it can be wrong. But for now, we'll just use, we'll use proof in both of these senses. Proof to mean an attempted proof and something that's actually correct. I guess that's a self-reference definition. An attempted list of logical steps that should reach the correct answer. Okay. All right, well, what's wrong with this attempted proof? Why, once I got to this step, can't I just do that? I mean, this is true, right? I mean, I've just rewritten it, t equals 1 plus 2t.
You added more. Like, I don't know. Like the pictures, it's true like the series matches, but the meaning of the T, like, is different. Like T t was supposed to be like an infinite series, and then like it's like you added it again when really you were just. I need
So
to.
I think you're saying I did some cheating.
You didn't define things correctly.
Yeah.
Yeah.
You changed the definition midway through the proof.
Yeah.
What definition did I change? I don't think I changed the definition midway through.
So
Technically
that's
not.
like super infinity. It's like angry, and you factor out a 2, and you could factor out an apple if you wanted to.
I mean, yeah, that's sort of true. But I mean, that's not necessarily a problem. I mean, say if this thing were convergent, it wouldn't be a problem. Let's say I did 1 plus 1/2 plus 1/4 plus 1/8, etc. And let me call a variable w equals this. Then I can do the same thing and actually find the answer, right? So I can have w equals 1 plus 1/2, so I factor out 1/2 from everything, and we get 1 plus 1/2 plus, etc. W equals 1 plus 1/2 w, 1/2 w equals 1, and w equals 2, like I want. So this technique can work.
As long as w does actually add up to 2, but.
All right.
What are you doing to us?
Dylan, so I have a friend, mathematician in the audience, who can perhaps elucidate these answers for us.
So the formal proof of the claim on the left depends on things we know to be true for real numbers or integers.
Yeah.
And we make the assumption that t is a real number when we use that claim.
Right. So I've not been very clear in this informal proof. It looked fine when we talked about it, because in some sense we were all assuming that I'm talking about real numbers. And if I were making a formal proof at some point, I'd have to define the domain of solutions that I'm looking at. So the key point of this is I also have the added assumption that S is null and defined. So if we look at this equation, this t equals 1 plus 2t, you can see that in some sense infinity is also a solution. Infinity certainly equals 1 plus 2 times infinity. And so we can't just conclude t equals -1 if we're looking at some bigger domain, or a domain which includes infinity. All right. Can someone give me a different solution? Yes.
Can you cover the difference between the phrases like countable infinity and not countable infinity?
I certainly can do that. I will cover that point after this. Okay. Right. So can someone see another solution to this equation? So I have infinity and I have -1. I want a different one.
Negative infinity?
Right. Negative infinity also works. Negative infinity equals 1 plus 2 times negative infinity. And in fact, with a larger domain, you can find other things that work with this. I mean, you find special numbers. Or you could even define numbers, which are just solutions to this. I shouldn't say numbers, I guess. Objects. Right. Okay. So this is the difference. This is sort of the danger of informal proof. I have to have some idea of what I'm talking about, and there's some assumption that we're communicating that you and I are both talking about the same thing when we discuss an informal proof. There's inherent understanding here of why the answer is -1, and there's inherent understanding here of why the answer is infinity. Okay, I guess I should briefly mention is that sometimes it makes sense to call this -1. You can sometimes sum infinite things usefully. So like maybe one that you've seen that's used in quantum mechanics a lot is this equation, -112 equals 1 plus 2 plus 3 plus 4 plus etc., which looks magical and is magical in the sense that it doesn't make any sense until you know what it's talking about. And what it's talking about is a continuation of the Riemann zeta function, which I analytic continuation of the Riemann zeta function, which I won't go into, not because I don't want to stun you, but because I don't understand. Yeah, and so, in fact, you can do the same sort of analytic continuation here, and you would get -1 usefully. I don't know how to use it usefully, but the internet tells me it can't be used usefully like this. There are different ways to sum infinite things. Sorry. So this is -1 under Cesar's sum, Abel's sum, and Ramanujan's sum. I can never say his name right. Is it Ramanujan? Anyway. Okay, yeah, so this covers my basic example. Alright, difference between countable infinity and uncountable infinity. This is definitely more of an aside to the talk.
Peter, I'm giving a talk on logic for this series, so you could push that off on me if you.
That sounds good. Come Dylan's time.
Suspense.
Thanks. Alright. So now I guess I will go into more of the basics of how we prove stuff. So we have a couple methods of proving things. We call them usually, let me just do 2 of them. Direct proof and proof by contradiction. They're screwy. So, I'm going to assume that some of you in the audience, oh wait, I don't have to assume it, have seen these concepts before. So I will ask the audience for a definition, though I will restrain my mathematician friend from answering to start with. Yes, I will, yeah, you can choose which one to give definition for, but not both.
Okay, I'm gonna go with proof by contradiction, because that's the one I struggle with the most. Is that where you posit that something is true and show that by necessity it is false, and therefore its opposite must be true?
Yes, sort of. You don't okay. Yes, there's also some understanding of how you show it's false. Okay, so proof by contradiction is, yeah, so you assume something. So you assume one thing that you're looking at, and then you can take all your other axioms as well and assume those as well. And perhaps other things which you know to be true already. And then you use the logical steps, and you get somewhere which tells you that something is wrong. You find that if your supposed assumption were true, then you would have that one of the axioms is false, or some other statement that you've already shown is true would be false, which means you have a contradiction, which means your assumption can't be true, which means it must have been false. Yeah, there's a lot of that. Okay, that's the basic idea of proof by contradiction. Do people need me to re-explain that? Are you okay with contradiction? Okay with contradiction. Direct proof. Who can give me a definition?
So 10-year lay on the side after Q, but your lab can only afford P. Therefore Q. But really, yeah, you want to prove Q. So you start with P, and then you just go through it. You start with P, and then you just make your way until you get Q.
You start with your assumptions, you go through the logical steps, and you get to the solution. Or you get to what you want. Alright. Now, let me show you a cool problem that we can do using a direct proof to keep your interest. Alright. So, you're physicists, right? So you like pictures, maybe? I like pictures. I do topology, or algebraic topology. Okay, so I take a sphere, a two-dimensional sphere for you pedantic people. And I have 5 points on the sphere, placed somewhere on the surface of the sphere. And I want to prove that some 4 of the points lie on the same hemisphere. What is a hemisphere? A hemisphere is just some half of the sphere. If I draw a circle around it, half of it will contain 4 points. Okay. I'm going to let you stare at this for a little bit. take some thought. And I should say these are tricky problems. These are not something you should feel dumb for not getting immediately. All right. First off, does everyone understand the problem? No. Okay. Yeah. So I have. Oh boy. Yeah. It's the problem with points. You can't tell which side they're really on. Yeah, just like my brother. Okay.
Draw circles around the ones that are on the near side and dotted circles around the ones that are on the far side.
Ah, that's a good idea. Okay. Yeah. So, we'll use different colors. Otherwise, we've got more dots than we want.
If you're already using a different color, can't you just use the green to make dots on the other side?
I could, yes.
We have any funding for the circles?
Okay.
Is the
And let me just.
is the middle dot like in the center?
No, it's not. So all of these dots are on the surface of the sphere. So I have a sphere. Oh no, I see no spherical objects. All right, I have a sphere. And
Physicists so hard.
topology so hard. And I have 5 dots. Okay, 5 fingers. 5 dots on the surface of the sphere.
Okay.
And I am somehow cutting the sphere in half, and I'm saying that 4 dots, if I look at all halves that I could draw, how can I phrase this well? I can cut the sphere in half in such a way that 4 points lie in one half. At least 4 points lie in one half.
Interesting. Okay.
Yes, okay. And my attempted cut here is the black hemisphere. I guess there's something I should to be technically precise, I should say closed hemisphere. So I'm also including the boundary points of this. So that's yeah.
Could you factor in surface area somehow and choose each point? And if 3 other points are within that surface area, half the surface area, then proof?
Yeah, so that would be one way that we might think to start. That's not the way I know to prove it. My guess is that it doesn't work. We'll see. So what is the surface area of the sphere? It's 4 pi r squared. So dividing it by 2 is 2 pi r squared. What do I want to do now? So somehow I want to draw a hemisphere centered at one of the points. Yeah, so I guess it's not clear to me how to proceed after writing down like the areas of the hemisphere are in the sphere. Yeah, okay, but certainly that's a good thought. Yes.
I was thinking something with great circles.
Yes, that is the way I know to prove it. Doing something with great circles.
At least
Bigger circle?
Great circles are just circles which cut the sphere into 2 equally sized hemispheres.
so there's some way that you can get 2 points on a great circle no matter what, right?
Yes. So if you pick an arbitrary 2 points on a sphere, there's a great circle that goes between both of these points. This is a useful fact. We are approaching the solution.
So if each of these is a point charge, you could use Gauss's law.
Well, no, if you get 2 on a great circle, then there's no way that you can redistribute points such that there's not 4 on one side, right?
Yeah.
Yeah.
So let me make that.
Hey! Ah, man, I should switch jobs.
You did it. See?
Experimental is going through.
Okay. So 3 colors. Okay. So yeah. So I take 2 of the points. Let me take these 2 points. Attempt the circle. Attempt circle is key. Okay, so what have I done? I have connected 2 points. Where are the other 3 points? That is the big question. So the other 3 points lie on one side of the hemisphere or the other side of the hemisphere. There's a key phrase I would like to use now. Does anyone know the key phrase I'm going for?
Ad nauseam?
Hmm? Ad nauseum? No, that's not the one I'm going for this time.
Pigeonhole?
Yes, I am going for the pigeonhole principle. Who among you has heard of the pigeonhole principle? Okay, I see people without their hands raised, which is good, which means I can explain it. So the pigeonhole principle says sort of that if you have some number of boxes and a greater number of objects, why did I choose that many? Oh wait, why didn't I just draw a fewer number of things and call them boxes? Okay. Okay. So I have this many objects I wish to place in this many boxes. The pigeonhole principle says, obviously, that some box must contain at least 2, because, like, you're squashed. Yeah, so this is the principle we're using here. We have 3 points and 2 boxes, the boxes being the hemispheres. So one of the boxes must contain at least 2. So some side of the hemisphere has 2 points, and we already have 2 points on the great circle we constructed, and so we have a hemisphere which contains 4 or 5 points. And we did this directly. We just proceeded through logical steps, where we can construct great arcs, and then we can use the pigeonhole principle to argue that at least 2 out of the 3 points must lie on the same side. And together we are done. Yes.
So because you said they were like closed hemispheres, do we just pick a side we want the dots in the line to be?
No, so they're on both sides. So since I have closed, since I've defined it as a closed hemisphere, so the points that are on the line are both in this hemisphere, in this closed hemisphere, and this closed hemisphere. Another way of saying it is the intersection of these closed hemispheres is exactly this circle.
Okay, so if they're on both, then how does one of the hemispheres only have 1 dot?
It has 1 or less dots. Oh, I see. Okay. Yes, you're right. Yes, my phrasing. No, my correct is not right. That is a good point. There are, in fact, 2 or less. Or sorry, at least 2 dots on the other side, but 3 or less. Between 2 and 3 dots on the other side.
Okay.
2 points. Yeah. So the way I phrased the question didn't quite have this problem. The way I phrased. In fact, okay, so if you want to be technically precise, I feel like you could do a wiggling argument just to be able to push the dots off the line and make things okay. I mean, this is actually how mathematics proceeds a lot of the times. You get something close, then you wiggle. Yeah, I'm not 100% convinced. Oh wait, no, a wiggling argument won't work because you have all the points be the same point, and you can't wiggle. No, you could. Okay, anyway, sorry. Okay. Yes, so I avoided this in the question by saying that show that 4 points lie in the same hemisphere.
Okay.
Alright, good, that was our direct proof question. Do you guys like direct proof more than proof by contradiction?
Yes.
Yes, definitely.
Strongly agree.
Why?
Because proofs by contradiction, like you said, you're flip-flopping a lot, and it's not just like, it doesn't just run up and punch you in the face and say, accept it. It's like, I'm gonna trip you, and then laugh at you, and your filth. I don't like that.
So I actually like it for the reasons you say you don't like it. In the sense that it tries to trick you and then you're like, no. And it's also fun just being sometimes like, because 1 + 1 doesn't equal 3, this thing was wrong. Okay. Who has a nice proof by contradiction? I want to try and solicit a proof by by contradiction.
Let's
I
do
will
the
come to
card
Dylan
out.
last if we are out of other audience proofs. But
Can we do that the universe is infinite
prove that the universe is infinite
by contradiction?
by contradiction.
Isn't.
Wait.
You
universe is
assume that the
defined.
universe, you want to prove that's not infinite, right? So
Yes.
so you assume that it is infinite and do proof of contradiction.
Okay, I don't know this proof.
Let's go
so
get the spaceship, guys.
We'll have to go here. Wait, so Zane, you've seen this proof, right? You're not just going to leave me out.
Yeah, cosmology class, yes.
Okay.
Sort of.
Alright.
We invoked a lot of
By
things.
observation, you can prove that. It's not really like.
So derive some
the
mathematical
geometry.
eyes.
Alright. Yeah, what now?
I know the answer, so.
Do the
Yeah,
proof.
and then
Well, what
you
is-
make Y and Z observations.
That's awful.
Sorry, I heard.
Basically, if the universe is infinite, you have certain observations that have to be true that don't occur.
Okay.
It would be
What?
not
Like, if you look in the sky, you don't see infinite amounts of light.
We should do this in proof form.
Wait, so why would that necessarily, I mean, that just says there aren't infinite many stars in there.
Yes, but the universe is infinite, and, you know, then there's no reason to assume that the density of the universe in terms of stars would change.
Well, I mean, that's,
There's also no reason to assume it wouldn't.
yeah,
Is there?
we sort of have to like
That
choose
would,
a worst
then you'd
case.
assume that you're in a special case.
Yeah, sure,
in the
let's assume that we're in a special case, the location of the universe, and that at some point there are a finite number of stars and they drop off.
I mean, most of us do it on most of the universe. That's the reason why we have this.
Wait, assume universe is infinite with same star density as we see in our local region.
Okay,
That's like,
okay.
that's like one
Is
of the
this
fundamental
the actual
pieces.
method that we want to use? I don't know the answer.
That'll work. So assume universe is infinite with same star density.
I mean, I know there are ways about it without it.
I'm telling you, we should have done the Cardano engine.
Yeah, that would work better.
The Conrad engine.
The Conrad.
Consider water as an ideal gas. Implication, black hole.
So, as a mathematician, I'm a little confused. Okay, I
Well,
guess.
you have to be able to define your universe, and so you have to be able to observe it in such a way that defines it so that that is true. And if you make, you know, like hand-wavy arguments like, well, not like hand-wavy, but make assumptions that like we're in a special location in the universe and things of that sort, then you can come to a conclusion that that isn't true. But
Let's just do square root of 3.
I don't know.
Okay, so yeah, so,
It lies in
alright, so my understanding is that if we assume the things that physicists want to assume about the universe, which we have good data to assume, then we have a contradiction. Yay, skip. Okay.
I forget the exact things. You can do it without making these assumptions, but
Yeah.
I forgot the exact details of it.
Alright, next time I'll make a note not to solicit questions in subject areas that I'm not familiar
Yeah,
with.
that's it.
Sorry. But thank you, Zane, for that suggestion. Okay. Let me do another one, a silly one. I'm going to prove that every positive integer is interesting.
Say that again?
I'm going to prove that every positive integer is interesting.
Interesting. What's the definition of interesting?
Why are you ignoring the negative ones?
I could
Not
extend it to
interesting.
negatives if I wanted to, but I don't want to. It's just a little technical. I mean, it just takes a little bit more work, and I don't feel like working.
So by definition of interesting, you mean
Okay.
that there's some attribute that we can
Yeah, so there's
attach
some
to each
property
number?
of the number that I care about. So like 1 is interesting because 1 times 1 equals itself, and it's the only positive integer to do that.
Okay.
2 is interesting because 1 plus 1 equals 2. 10 billion and 3 is interesting because I just thought of it. There are a lot of ways you can define interesting.
Okay. It's very arbitrary. What if somebody else decide to do this? What, and their definition of interesting
Well,
was
isn't that the
different
Yeah,
than.
so my definition of interesting is purposefully loose. This is a sort of fun proof, as
Okay.
opposed to a technically precise thing. Sorry.
Okay.
Let me let you mull on this for a second and grab some water.
I want that one. Please don't.
Good mulling team.
This is how we roll.
Don't know. Probably so.
All right, so I guess you already have a hint that I'm going to try a proof by contradiction.
Good God. And here I was thinking I'd have some for breakfast. Oh, look, there's one left.
Yeah, and I want to reiterate, as Zane said, this is not a very usefully defined property here, as we'll see in a moment. I mean, since every positive integer is interesting, maybe this interesting thing itself isn't very interesting. Okay. All right, so proof by contradiction. What do I want to do as my first step?
Say every positive integer is not interesting.
Right.
So-
What does that
Or
mean?
there is one that is not interesting.
Yeah, there is at least one which is not interesting. Okay, good. What can I do from there?
Find it.
Well, the fact that it's not interesting, and it's the only one that's not interesting.
It may not be the only one.
Choose the lowest integer of that set of non-interesting numbers.
Yeah, we're going to use the well-ordered property of integers. We can write integers in a list. And so, okay, well, let me elucidate Connor's point. So, in fact, yes, this is the solution. Okay, I will say a lot of words, but I won't actually say the solution. I'll let someone else put it out. So, the first thing we do is assume this is false, that there exists some positive integer which is not interesting, doesn't have this interesting property. Okay, so among the set of such integers, there must be a smallest one. Why? Because I can just write all of these integers in order from smallest to largest. Okay, from smallest to upwards. And so there must be a lowest one. Okay. So there exists a smallest non-interesting number. Right? This is a contradiction. Why?
Because that's an interesting number.
Yeah, this is an interesting number. It's the smallest non-interesting number.
So then you can just,
So there can be no smallest non-interesting number, which means, or sorry, I should say integer, positive integer. So all positive integers must be interesting. Boom.
So what problems do you run into since now that number is not non-interesting? Now the next number up in that set of non-interesting numbers would be that would be the smallest non-interesting number. So that removes that attribute from the original smallest non-interesting number. It's now non-interesting again.
Yeah, but it was interesting in the sense that it would have been the
It was like a fad.
smallest
Oh my
non-interesting
It's just a
number.
trend that.
That's kind of like cheating.
Yeah, so I mean, so this problem is silly in the sense that my interesting property really doesn't make that much sense. It's if I can identify a number somehow, then it's interesting, and I can sort of identify all numbers.
Fair
And
enough.
using the axiom of choice, I could do this with reals as well. I could well order the reals, and then I could do the same argument. We could also extend this to negative integers by with this idea by defining smallest. We could just write a list. We could write 0, then -1, and then 1, and then -2, and then 2. So we have an ordered list here of all the integers, and then we can pick the one that's to the leftmost in this list, and that would be our contradiction. Okay, so yeah, this is all the material I had prepared for the talk. I guess what I want you to take away is that proof for most mathematicians means convincing people, convincing yourself when writing it down, and convincing others when they read it. Though there is definitely a basis in a stricter notion of deriving everything in very formal logical steps. I don't know if you're going to talk about this at your talk, Dylan, or if you're doing different stuff.
I can.
I mean, I don't want to, like, this is what you're going to talk about at your talk. Okay, well, I'll leave it there. I would say that the most common methods of proof are direct proof and proof by contradiction, of which I've given you 2 of the more fun problems. Most problems you actually run into will be more pedestrian. These are, yeah, so these, let's see. I saw the sphere problem as a competition problem, an old competition problem, and this interesting property was told me by a friend a while ago. Yeah, they're not everyday problems, but they're, yeah, I think they're good examples of methods of proof. Oh, right, and the other thing I showed you was that with our informal proofs, we sort of have some understanding of what we're talking about when we're communicating ideas. And it may not be, what we've said to each other may not be true in all contexts, because we're not being completely precise. That was the infinite sum part of the talk. Okay, thank you very much. And if you have any questions, I will be here.
Can you have direct proofs and proof by contradiction in both formal and informal proofs?
Yes, I think. So I myself am not very familiar with formal proofs. But yes. Any proof that you can write down, you can in principle write it down with formal.
Okay. And how strict are formal proofs? I mean, what level of defining and attributing do you have to do?
I think I'm not the expert in this audience on that question. I think Dylan is more suited to answer that question than me.
It's extremely strict.
Okay.
Yeah, so I mean, I guess we can get it somewhat. Yeah.
The level of strictness you should imagine is something you could feed into a computer, and then it would say your proof is a good proof.
Yeah.
Okay.
So like if you take formal logic systems, I mean, yeah, so a proof in a formal logic system looks something like this. I don't know, do they even have symbols? I feel like they do. Okay, so I don't know formal logic, but it really is just strings of symbols.
Okay.
So this is actually a good definition of the difference. So formal logic goes from step to step. In an informal proof, there's usually some worded justification to explain what's going on.
And you can skip steps if they're like inherent knowledge things, like
so
addition and subtraction. Like you didn't outright show the subtraction of the s.
Yeah, right,
Mm.
exactly.
Okay. Where in a formal proof, everything.
Yeah.
Step by
you'd say
step by
this,
step.
This is, yeah, exactly.
Okay.
And even in informal proofs, there's some notion of rigor, which is sort of like how many of the sub-steps you're showing.
Okay. Thank you.
Yeah. Yes.
In real math, you don't always know the theorem you're trying to prove beforehand. So how do you, like mathematicians, go around feeling around possible theorems that you could prove?
In my opinion, it's mostly just guessing until you hit on a good idea. So like when you're trying to prove that sphere problem, Zane posited a good idea to start with, some argument of area based on where the points were. And it didn't pan out. Sometimes that happens. Most times that happens, I think. And then we move on to different ideas and perhaps return to old ideas and try stuff out. I guess there's something more here to say, though, that theorems and proofs don't really capture all there is to say about certain problems. When you're dealing with mathematical problems, you really want to have some much fuller understanding of what's going on than you would get out of just writing a proof. A proof is really like knowledge as opposed to understanding. And when you're a mathematician, you want to understand the problem so you can write proofs. In fact, in order to write proofs, you usually have to have some deeper understanding of the problem and how the interplays between the structures of the problem.
Can you think of any notable proof that was proven before an applicable problem was found? Does it ever go in reverse like that?
Well, all sorts of math, like in
So
physics.
It seems a little problematic because whenever you have a proof, you're dealing with some problem, so there must have been something to solve.
Well,
I guess but you can certainly, like, mathematical structures have appeared before they've had practical use. I mean, the common one is the example of I. It was used in mathematics a lot before it was used in electrical engineering, which is, I mean, it's needed these days.
Mm-hmm.
Like particle physics, like you math people did groups a long time ago, and then particle physics, they found out that particles were groups, so that was really helpful.
So theory can far precede practical usage. But I would say anytime we come up with something, we are trying to solve a problem, though probably it's not going to be the most useful problem that solves. Or maybe I shouldn't say probably. It could not be the most useful problem that solves.
Okay. Any other questions?
All right, thank you.
Thank you.